Modern computing systems ingest millions of data points every millisecond. For a machine to actually process, retrieve, or make sense of that incoming avalanche of information, it has to organize it. The most obvious way to sort a list is to force the computer to compare the first unsorted item to the second, then the third, and so on. It repeats this comparison for every single item against every other item in the dataset. This chart plots dataset size against processing time to illustrate the problem with that naive method. The data grows at a steady, linear rate, but the processing time is a sharply spiking exponential curve. In computer science, this is known as time complexity. As a dataset reaches into the millions, the time required to cross-reference every item multiplies until the system effectively freezes. There is also a strict physical limit to consider: memory. Many traditional sorting methods require the computer to copy the entire dataset into a temporary holding area to organize it. If you have 10 gigabytes of chaotic data, you suddenly need 20 gigabytes of memory just to sort it. Solving the problem of scale requires an entirely different approach. The computer needs a framework that organizes data directly where it sits, without ever attempting to calculate the whole picture at once. That framework is an algorithm called quicksort, and it operates on a strict paradigm known as divide and conquer. The logic of divide and conquer is straightforward. You take a high-volume, computationally taxing task and break it into isolated, bite-sized fragments. You repeat this fracturing process until the problem essentially solves itself. The interesting thing about quicksort is that it doesn't actually attempt to sort the whole dataset. It merely fractures it. Look at this horizontal row of square blocks. Each block contains a different size and value, and the entire row is completely jumbled. The algorithm begins by selecting one single element to act as the pivot. It chooses this pivot at random, which prevents the algorithm from slowing down in cases where the data happens to already be partially sorted. Now we enter the partition phase. The algorithm scans the rest of the array. Any value smaller than the pivot is forced to slide over to the left side of that illuminated block. It performs the exact opposite action for the remainder of the data. Any value larger than the pivot is shuffled to the right side. At this stage, the left and right clusters remain completely unsorted internally. They are simply grouped based on their relationship to the pivot. However, the pivot itself is now in its permanent position. Because every element smaller than the pivot is now to its left, and every larger element is to its right, this specific point in the array is the pivot's mathematically correct final home. By making one single decision, the algorithm perfectly finalizes one piece of data and effectively cuts the remaining workload in half. Now the algorithm creates a strict boundary. It ignores the locked pivot and the right side, focusing exclusively on that isolated left subarray. This cascading tree structure shows the recursive trigger in action. Quicksort calls itself on this new, smaller array, picks a brand new pivot, and runs the exact same partition process. The array splits into two smaller subarrays, which immediately split again. The dataset fractures into continuously smaller, increasingly isolated fragments. It is a continuous zoom inward, halving the scope of the problem over and over. Eventually, the algorithm hits a wall. This is known as the base case, which occurs when the subarray is fractured down to just a single element. A single, isolated element has nothing to be compared to. Therefore, it is considered sorted by default. By relentlessly shrinking the scope of the problem, the algorithm forces the data to eventually sort itself through sheer isolation. As the downward journey halts at the base case, the recursive calls resolve. The algorithm steps back out, seamlessly stitching the isolated fragments back together. Because every single pivot locked into its permanent home on the way down, the entire massive array is perfectly sorted by the time the process returns to the top. This efficiency is why Quicksort is the default sorting engine behind major programming languages. It is the underlying logic used by standard libraries in both Java and C++. Furthermore, it accomplishes this through in-place sorting. Because the slicing and moving happens entirely within the original data space, it uses very little extra memory, making it highly hardware efficient. Quicksort demonstrates that the most efficient path through a complex dataset is not to solve the whole array at once, but to fracture the task into pieces so small that they essentially solve themselves.